A very good day to one and all present here. I am Yukta Ramesh, a student of Manipal Institute of Technology, Bengaluru. I am here to present the paper titled MetaRec, a meta-driven strategic semantics-oriented model for recommendation of software requirements. I am also presenting this paper on behalf of my co-author, Dr. Gerard Deepak. Coming to abstract, this model uses pre-processing of query words onto which entities from the Wikidata are harvested. Wikidata comprises the World Wide Web knowledge. The model encompasses categories, strategies like classification of dataset using decision tree and classification of metadata using LSTM classifier. The overall framework has a maximum mean precision, accuracy, recall, F measure, and the lowest value of FDR, making it the best-in-class strategy for software requirement recommendation. Coming to motivation, this framework has been proposed due to the lack of standard framework that is semantics oriented and comprises auxiliary knowledge for recommending the best possible software required. Most of the existing models of these models are aggregated systems. Requirement recommendation models are very few. So owing to this, there is a need for knowledge-centric requirement recommendation in the present era, which is the primary focus of the paper. The novel contributions of MetaRec are that the strong model like LSTM is used to classify the metadata and integrate it into this model. The decision tree is to classify the interdomain requirement specification documents, and dataset collectively is a novel contribution. Similarly, computation using COSIM rank and Pylos evenness index in the model at different stages is also normalized with threshold and step deviation measures, and this metadata encompassment into the framework is nobility in the model. Now moving on to related works, we have our first author, Felfernik. I'm so sorry if I'm mispronouncing their names. So moving on to the methodology, they have introduced recommendation and decision technologies for prioritizing requirements. We name this for our convenience, we'll name this model the RRD model. So what exactly this RRD model lacks is that they use online forums for assimilating and discovering features. And the other evaluations are done based on the capital requirements, and the system only acts as an interface. And thereby there is no strong mechanism for evaluating and recommending the model. The model is only 85% valuable, and we require an automatic model for requirement discovery. Therefore, this model does not perform as expected. Next, we have the Mulla. Again, I'm sorry. They have introduced the K nearest neighbor algorithm to prioritize requirements, addressing communication issues and bias prioritization. This model lacks learning model for a semantic, which is similar for system security that can be enhanced, and the skip thought models don't work well. Moving on to the next author, let's name this the RSS model. Then they have presented an analysis and recommendation system to align providers and consumers on non-functional requirements. The RSS model does not perform as foreseeable as it uses recommendation systems to support software requirement felicitation, where subject matter experts collaborate on a topic mainly with the stakeholder. This model is again 85% manual. This makes the MetaReg model very efficient because although it is a query-initiated model, it is also a knowledge-driven and aggregated by several heterogeneous models. So making this the best-in-class model again. The proposed system architecture. The figure depicts the meta-reg architecture semantically inclined requirement recommendation framework, which is driven by the user query or topic. The user query or topic is where the input is consigned to the pre-processing. This includes the standards from the Python's NLTK package, which involves tokenization, lemmatization, stop word removal, and also named entity recognition (NER). Once the pre-processing is done, the individual query words are obtained from the standard libraries of Python's NLTK framework that have been incorporated in the model. At the end of pre-processing, we have the discrete query words. Query words is subject to Wikidata API. Wikidata API is a knowledge that is collected from several heterogeneous sources and is integrated into a common platform, that is the Wikidata. So, along with NER, named entity recognition, the query words would determine the context. However, this is not sufficient. So, therefore, the domain ontology, which is generated using the categorical terms from the dataset and is also merged along with the entities harvested from the Wikidata API. Also with the pre-processing query words and to link the domain ontology with the entities from the Wikidata and query words. The lin similarity is computed with a threshold of 0.5 and a large number of terminal ontology nodes that are linked together, which is further used in the framework. Here, the dataset as an input is given to a tool named OntoCollab. We use OntoCollab as a tool and the domain ontology up to 5 levels, excluding the individuals that are generated. However, the knowledge is harvested from several other sources like metadata, and henceforth up to 5 levels of restrictions of the domain ontology are achieved to preserve the deviance of the terms of entities in the ontology from the primary domain. The data set of required has made the categories in the dataset are used as the input to a customized agent-driven focus crawler, which inputs the categorical term from the dataset and a multi-agent based customized crawler that crawls a block and the software requirement specification document about the domain of the dataset from the World Wide Web. The inter-domain documents are crawled into all the software requirement specification document, which is arranged based on the term proximity are stored as a hash map with keys as categories. The keys also comprise the keys within the documents and values in the documents themselves. So a multi-key level attribute function is designed to preserve it as a hash map where the key terms are relevant. The value is linked to a document itself. The reason for organizing it to the key value structure or in the form of hash map is to ensure that the software requirement specific document is stored as a thesaurus based on the dictionary term. Further, the retrieval becomes easier. Henceforth, this arrangement is followed. To extract informative terms, TF-IDF is applied to the collection of documents wherein terms which are frequent to the documents and the terms which are rare across the documents are yielded through the TF-IDF. However, informative terms and the dataset categories are extracted as well as the terms extracted from the TF-IDF model are all integrated to form an informative term set. This term set further drives the model and is provided as input to generate metadata. Metadata is generated by using metadata generator, namely a meta tag harvester and open catalysis. This metadata cannot be handled due to a large voluminous content as it has to be as it has due to the as it has to be classified to further handle it, and classification is achieved using the strong deep learning. Long short term memory LSTM works well with the large volumes of data like metadata. Hence, it is preferred here, and as it works on the fundamental of auto-crafted feature selection. Next, we have the COSIM rank threshold, which is empirically set to a very stringent value of 0.8. Similarly, the Pilus evenness index is also a very strong recollection computational measure, is set to a step deviance of 0.15. The features are selected from the domain ontology Wikidata, and Shannon's entropy is set to a step deviance of 0.25 as a good number of relevant entities must be passed to a decision tree classifier. A decision tree classifier can be defined as a visual representation of all solutions to a problem given constraints. Coming to implementation, the proposed framework has been implemented using Python 3.10. The TensorFlow library was configured for realizing deep learning strategies like LSTM. Python's NLTK library is utilized to carry out several natural language processing like tokenization, lemmatization, and other standard NLP tasks. Open catalysis is used to add metadata into the framework. Coming to the performance analysis, here you can see that the proposed meta-reg has the highest mean precision, mean recall, mean accuracy, and mean F measure. It has the lowest FDR. FDR stands for false discovery rate. It quantifies the number of false positives, and inherently FDR quantifies the error rate in the model, which you can see here is only 0.06, lower than any of the models mentioned above. So moving on to the performance analysis of the graph, here we have precision versus number of recommendations, and first we see that the meta-reg occupies the highest hierarchy of precision with 94.81%, and then is the RSS model with 91.21%, and then the COMS model with 87.54%, and last the RSS model with 84.26%. So yeah. To conclude, this paper proposes a strategic knowledge-driven framework for requirement recommendation specification. The encompassment of the domain ontology to which the dataset and the requirement document belong to is funneled into the metadata generation framework and is subsequently classified using LSTM. The presence of NPMI, COSIMRank, and Pilus evenness index in the framework helps in semantics-oriented reasoning and learning. The Shannon's entropy also helps in feature selection and construction of decision tree. The LSTM provides a strong learning infrastructure. The framework has an overall mean precision of 95.56% and a mean F measure of 95.55 and a mean precision of 94.81, making it the best-in-class model for requirement recommendation. These are some of the references I have gathered for requirement recommendation, and yeah. Thank you for your time. Thank you for listening to me. Thank you for letting me present. Thank you.